Hey everyone! Today we are diving into one of the most important ideas in all of machine learning, regularization. Seriously, this is the secret sauce that takes an AI model from being just a good memorizer to being, well, actually smart. It's how we build AI that can think on its feet. But let's kick things off with a question that trips a lot of people up. How is it possible that a model can get 100% on its training data, a perfect score, and then be a total failure when you deploy it in the real world? It just doesn't make sense, right? Well, this is the exact problem we're going to solve today. All right, so let's get into it. The villain in our story today has a name: overfitting. This is what happens when a model doesn't just learn the data, it learns it way too well. It gets obsessed with every single quirk, every random bit of noise, and it ends up memorizing the training set instead of understanding the actual pattern. Here's the best way to think about it. Imagine a student who's prepping for a big exam. Instead of learning the material, they just memorize the answers to the practice questions word for word. Of course, they're going to ace the practice test, but the second you give them the real exam, where the questions are just a little different, they're toast. They completely fall apart. That student, that's your overfit model. So this table really lays it all out. You've got three scenarios. On one side, you have an underfit model. It's way too simple, it misses the point entirely, and it fails everywhere. On the other extreme is our overfit model. It's way too complex, a genius in training, but a dud in reality. And right there in the sweet spot in the middle is what we're aiming for, a model that generalizes. And regularization, that's our ticket to getting there. So how do we actually stop our model from overfitting? Well, if overfitting is the villain, then our hero is regularization. And the idea behind it is actually beautiful in its simplicity. We're going to penalize the model every time it tries to get too complex. We're basically teaching it a new rule. Simplicity is just as important as accuracy. And here's the more official definition. Regularization is a technique where we add a penalty to the model's loss function. Now, don't let the term loss function scare you. It's just the way a model scores itself on how many mistakes it's making. So by adding this penalty, we're changing its goal. We're telling it, look, your job isn't just to get the right answer. It's to get the right answer in the simplest way possible. And this slide just shows it perfectly. Before, the model's entire world was minimizing its error. That's it. But now it's a balancing act. It has to keep the error low, sure, but it also has to keep this new complexity penalty low. And that trade-off is everything. It forces the model to ignore the noise and focus only on the features that truly, genuinely matter. So, how does our hero actually do this? Well, it turns out regularization has two main powers it can use. They're called L2 and L1 regularization. They both have the same goal, fight complexity, but they do it in really different and fascinating ways. First up, we've got L2, which you'll also hear called ridge regression. L2 adds a penalty based on the square of the weights of each feature. The effect is kind of like a gentle but persistent pull, shrinking all the feature weights down towards zero. It makes less important features less influential, but it never pushes them out completely. It kind of believes every feature has something to contribute, even if it's tiny. And in practice, what does this give you? A really stable and dependable model. L2 is fantastic for making your predictions more consistent. And it's especially good when you have a bunch of input features that are all kind of related to each other. It's the reliable workhorse of regularization. And then we have L1, also known as Lasso regression. And this one's a different beast. It adds a penalty based on the absolute value of the weights. Now that sounds like a tiny change, but whoa, does it have a massive impact. Because of how the math works out, L1 can actually shrink some of those feature weights all the way to zero, like flat out zero. And that leads to something amazing. L1 regularization basically does feature selection for you, automatically. By setting the weights of useless features to zero, it's literally kicking them out of the model. This creates what we call a sparse model, a simpler, cleaner model that only uses the most important inputs. This is a game changer when you're working with data that has thousands of potential features. Okay, so which one should you actually use? This table is a pretty handy guide. If your main goal is to simplify your model and you suspect a lot of your features are junk, L1 is your friend. If you care more about overall stability and you want to keep all your features in the mix, L2 is probably the way to go. But what if you want the best of both? Well, that leads us perfectly into our final technique. It's a hybrid approach, a clever combination that takes the unique strengths of both L1 and L2 and puts them together into one super tool. It's called ElasticNet, and it's pretty much exactly what it sounds like. You're not forced to choose between L1's feature selection and L2's stability. You get both. It actually gives you a control knob so you can dial in the perfect blend of the two penalties for your specific problem. And you can see right here why ElasticNet has become so incredibly popular. You get that awesome feature-killing power from L1, but you also get the model stability and robustness that comes from L2. For a lot of data scientists, this is the default go-to choice when tackling a new, messy, real-world problem. Okay, so let's pull this all out of the world of theory for a second, because this stuff isn't just for textbooks. Regularization is humming away behind the scenes in a ton of the technology that you and I use every single day. Think about finance. It helps fraud detection models zero in on the real signs of a scam instead of getting distracted by random noise. Or healthcare. It can sift through thousands of genetic markers to find the few that are actually predictive of a disease. From setting prices on e-commerce sites to deciding who gets a loan, regularization is the unsung hero that keeps these critical systems from going off the rails. So if you remember just one thing from all of this, let it be this quote. A good model fits the data. Anybody can build a model that looks good on the data it was trained on. But a smart model generalizes. It takes what it learned and applies it to new situations it's never seen before. Regularization is the bridge between good and smart. And I'll leave you with this final thought. The next time you're building a model, or even just using an app powered by AI, ask yourself, what hidden noise, what weird random correlations might this thing be learning? And how can we use these powerful techniques to help it see the forest for the trees?